This conference will now be recorded.
Yes, good morning everyone. Whether it's audible online, that's audible.
Yes, sir. Yes, sir.
Yes, sir.
Yes, welcome to Physical Design demo. So if you want to have attend the phone calls, right, you can attend outside. So what we will discuss in this demo, right? So we'll discuss all these things, overview of physical design. So all these things will come under the category of overview of physical design. All these things. This total PD we'll discuss. Next we'll discuss about our course structure at the last. How our course structure is, how our course has been totally structured. Then we'll discuss about placement support and interview preparation, right? And at last, any queries you have regarding placement support, even we'll discuss them. This is what the total three things I'll going to discuss. One is totally first thing is what is PD, right? And what we do in PD and PD course structure. That is what the first thing. Second thing I'll discuss about this PD course structure means what is the syllabus. It is physical design course structure. Here means how we will take the session, when we'll take the session, whether per day 3 hours a session will take, right? So we have two categories of courses. One is basics, another one is advanced level. So all those things I'll discuss in the physical design course structure. Third thing is about placements and your queries, whatever you have, right? This is about your this is what main agenda of my discussion is. So first, overview of physical design. What is physical design? So that is what we are going to discuss today. What is physical design and what we do in physical design, right? So before going to understand what is physical design or what we are going to do in physical design, right? So before understanding this, so we will discuss about chip fabrication and chip design. So what is chip fabrication and what is chip design? So who is going to fabricate the chip? We design engineers, we are not involved in fabricating the chip. Foundries are involved in fabricating the chip. What is foundry then? The foundry is a place where chip is fabricated. That place is very neat, clean, and well sophisticated. It has well sophisticated machineries. See, chip fabrication happens in nanoscale. Nanoscale means 10 to the power of -9. Even the transistors you cannot see through your eyes. You should see only through the complex microscopes. That much sophisticated as fabrication unit should be. So you can see some main foundries like TSMC, UMC, Global Foundries, SMIC, Intel Foundries, Samsung Foundries. So all these foundries majorly we can see outside the India itself. But we have even few companies where doesn't have foundries, but they depend upon this Qualcomm, AMD, and all, right? They will depend upon these companies. This Qualcomm and all, they'll depend upon these foundries for the chip to be fabricated, right? Now My question is, chip is fabricated in the foundries. It happens in a nanoscale, which is very complex. It should be very sophisticated, very neat, clean. So India, even today, right, it often doesn't have sophisticated foundries. We have foundries for research and development purpose. We have foundries, but we don't have sophisticated foundries. Sophisticated means production of mass scale of ICs. We cannot produce ICs in the mass scale, but for research and development, we have foundries. But we in India, we mainly involved in chip design, not in chip fabrication. So, what is chip design then? So, in chip design, mainly we use EDA tools. Right here, mainly we are going to use the EDA tools. What is EDA? Here, mainly, right, you can see here we mainly use EDA tools. What is EDA stands for? EDA example for EDA is design compiler, IGC2, Innovus Fusion compiler. What is EDA stands for? Electronic design automation tools. Means all these are softwares. So give me 1 second. I am getting this notification and again when everyone is joining. So I'll just remove it. Third. Notification. So we design engineers, we are going to design the IC by using what EDA tools, means software tools. So we design an IC and what we will give to the chip fabrication team. We design IC, but they fabricate IC. We are designing IC by using what? Laptops, softwares. So the softwares are examples are what? Design compiler, ICC2, Innovus, Fusion compiler. So we use EDA tools. So we design engineers, we design an IC, and what we will give to the fabrication team, so the fabrication team will fabricate IC for us. What we hand over to them. Yes, good, right? We are going to hand over GDS file. We hand over them what file? GDS file. GDS2 file. GDS stands for Graphical Data Stream Information Interchange. So GDS stands for Graphical Data Stream Information Interchange. So chip design team will hand over the GDS file for chip fabrication team. Then what is GDS? What is content of GDS? See, in chip fabrication, fabrication of chip happens. We design team, we are going to design the IC. So everyone know what is IC, right? This is IC.
Yes, sir.
This IC. Integrated circuit. Right? So everyone knows. So we are designing an IC, but what we hand over a GDS file. After that, they are going to fabricate. Then what is the content of GDS file? What is present in GDS file?
The layout design of
We have layout of cells. I don't know how many of you are aware about layout. How many universes have layout or not? I don't know. Right? We have layout of cell. So what is layout? So this is an example of layout. GDS file has layout. This is a layout of what? CMOS inverter. This is a layout of CMOS inverter. What is CMOS inverter as? It has PMOS and
NMOS.
NMOS. This is VDD, this is
Ground.
VSS, this is VIN, and this is VOut. So for the CMOS inverter, we will write this layout. So if you see your CMOS inverter, right? What CMOS inverter has? It has, if you write the fabrication steps, first your CMOS inverter, first it has what? P substrate. Inside P substrate, what is formed? Yes, you are going to form the N well. One N well is formed here. What is this? This is N well. And inside N well, you are going to form the PMOS, right? PMOS source and drain, you are going to form. Source, P plus region source, and you're going to form what? P plus region drain. So here you have silicon dioxide. On top of this, you have what? On top of this, you have polysilicon. Gate. This is gate. This is silicon dioxide. And in NMOS, in P substrate, you're going to form NMOS. This N plus region, this N plus region, and this silicon dioxide, and top of this, we have gate. So this is what? What is it? This is NMOS. What is it? This is PMOS. What we see from the top, only from the top, what we can see, that representation is called as what? Layout. So in the layout, what is this? This purple color is what? This purple color is N well, right? This white color is P substrate. This white color is P substrate. This purple color is what? N well. So inside the N well, I have to form the PMOS. So this is a diffusion, right? This yellow color is diffusion. This is P plus region. This side is source and this side is what? Drain. This is source. This is drain. So this is source. This is what? Drain. In between red color, what you are seeing, this is called as what? Gate. This gate. Polysilicon. This is polysilicon. So if polysilicon is crossing diffusion, this yellow color is P diffusion, P plus diffusion, right? If polysilicon is crossing P plus diffusion, a transistor is formed. So this side is source, this side is drain. Any side you can use source and drain. So this green color is what? N plus diffusion. This side is source. What is this? This side is what? Drain. So here you can see the gate and gate is shorted, right? The input is what? Gate, correct? This is gate. This is what? Source, drain. This is gate, drain and source. Here gate and gate is what? Shorted. Here we are shorted gate and gate. This gate and this gate both are what? Shorted. Next, this source is connecting to what? VDD. So this is the source side. This source is connecting to what? VDD. So we have to make connection through contact cut. This is a contact cut because this is a diffusion. This is a polysilicon. Source is what? Source is a diffusion. It is a polysilicon. It's a P-type semiconductor. But this is a metal layer. VDD is what? Metal layer. If both are connecting, I have to make one contact cut here. Again, this side, NMOS source is connecting to what? VSS. So this NMOS source, right, is connecting to what? VSS. And PMOS drain and NMOS drain, both are what? Shorted. So here this drain of PMOS and drain of this one, both are what? Shorted each other. So where input and input is shorted, right? That is taken as what? V in. Where output and output is shorted, that is taken as what? V out. So this type of representation is called as what? G layout. So inside an IC, sorry, inside a GDS file, I can find the layout like this. Layout of inverter. Layout of what? NAND gate. Layout of XOR gate. Layout of MUX. And its connections. Connections between these things. Connections between the layouts. This is not a box. What is this? This is a layout of inverter, NAND gate, OR gate, XOR gate. Then what is the content of GDS? So layout of cells and its connections. That is the main content, right? So main content of GDS file. I'll also it has a layout of cells and its connections. See here I am repeatedly using a word called as what? Cell. Cell is equivalent to gate. Right? Gate and cell both are what? Same. So it has layout of cells and its connections. So I have shown layout of only one cell, but GDS has number of cells and connection between them. See, you will write a diagram like this, right? If I ask to write any diagram, you write like this: AND gate is connecting to another GAND gate. You write a diagram like this. But GDS, instead of this shape, you will be having what? Layout. And connection happens through metal layer, right? So this type of information is present in GDS file. So now at last we understood from our explanation.
Why
We,
GDS2?
I'll come to your question once again.
Why GDS2 it is represented, not simply GDS?
See, actual full form of GDS is graphical data stream information interchange. Instead of calling II, they call it as GDS2.
Okay.
Graphical data
Graphical.
stream information interchange.
Okay, that is why it is GDS.
Yes, instead of calling GDS II, they will call it as
Ah,
GDS2.
okay.
Information interchange.
Okay, okay. Yeah. Thank you.
So we chip design engineers ultimately at last we give GDS file for chip fabrication team. So chip fabrication team will fabricate IC for us. Then how this GDS file comes? From what we'll start our design. End is GDS. What is the starting point? To understand this, right? Then we should go with ASIC design flow. This is your ASIC design flow. So last is chip design, right? For chip fabrication, we'll give what? What? Oh, that is white color. We're not able to see. Okay, we'll modify next time. If I sit and modify now, it will take a lot of time. So this is specification. This is architecture. Specification and architecture design. Both are almost same. Next is RTL design. RTL design. Next is RTL verification. Next is synthesis. Next is TFT. Next is partitioning. Next is floor plan. Next is placement, right? Placement, CTS, routing, sign off, fabrication, packing and testing. Next is final chip. This is partitioning. See, just I written briefly because this is not visible in the projector because of light. So this from here to here, right? Majorly we call it as front end. This is called as front end. Means only I am telling these steps. These are called as what? Front end. So from here, from synthesis till sign off. Fabrication means it happens in foundry. So design team will stop here till what? Sign off 6. So all these steps is called as what? Back end. Okay, now we'll start with specification and architecture design. Both are almost same. What is specification? So from where the design starts? Design starts with what? Specification. So specification means mainly entire chip. We decide what blocks are required in chip. So we require a ALU, arithmetic logic unit, ASIC, GPU, graphical processing unit, CU, control unit, USB, Wi-Fi module, Bluetooth module. So what are the blocks required for each entire IC to be implemented means what are the blocks required in that IC. First we will decide that. So again, apart from that, we'll also decide many items like what is a block area and chip area, right? Each block will take what is a how much area and what will be the total chip area. All these things are estimated. How they can estimate from the previous project experience? Only experienced person can do the chip architecture or do the take the chip specification. So you want this IC, okay? You want IC for mobile phone application. What are the blocks should be present inside an IC? How much? What is the area? What is the estimated power consumption? What is a clock frequency? Each block will work with what clock frequency? ALU, what is the clock frequency? GPU will work with what clock frequency? So for all these clocks is produced from a component called as what? PLL. PLL is called as what? Phase lock loop. What is role of PLL? Producing clock. This block requires a clock of 300 megahertz. Your PLL will produce. This requires a clock of 1 gigahertz. Your PLL will produce. So role of PLL is used to produce different clock frequencies. So each block requires what clock frequency? What is the cost efficiency? How much cost for the total chip designing? What is the cost? So all those things they will estimate in chip specification. So after knowing each block, right? After knowing each block, what block is required, then each block we should start designing. How we'll start with designing, how the design starts. Design starts with RTL design. Why RTL design? RTL means either we use Verilog or VHDL. So Verilog or VHDL. Those are hardware description languages. So we use either Verilog or VHDL to describe any circuit. Why? Why Verilog or VHDL?
Describes the hardware.
Yes. Anyhow, speed and all depends upon the components what we use during fabrication. That is second thing. Why we have to use Verilog or VHDL? Why can't I see, for example, I have one mux, just to assume mux. Why I should write that mux in Verilog or VHDL? Why I can't directly write the circuit?
It's simple, is it, compared to complex key?
Yes, your answer is almost near. Yes, the
Okay.
reason is simple reason for that is Verilog or VHDL will allow you to write the description or allow you to start the design by describing the behavior of a circuit, not the internal structure. You can describe the behavior of a circuit. If I ask you, people, tell me the internal structure of mux, how many of you can tell? 2:1 mux. By using gates, I'm not using any transistor level. By using gates, how do you implement 2:1 mux using gates?
By
We'll be
using
using
gauge.
AND OR and inverter.
Yes, correct. But how many can you do? Okay, leave about that. If I ask the question, same question, tell me the truth table of mux. Just simple truth table. Mux has what? I naught, I1 and select line.
Select line.
And output is Y. So what is the truth table here?
Whenever the
If select
select
If
is
line
select
is
line is
0, then I
0,
naught
low,
is
Y is
selected.
going to take what?
I not,
I naught. If select line is 1, output Y will take what?
I1.
I1. So
I1.
everyone remember this, right?
Yes, sir.
Everyone can remember the behavior of a circuit, but not the internal structure. So Verilog is allowing you to write the behavior, right? Use if statement. If select line is equals 0, then what your Y is going to take? Y is going to take what? I naught. Else Y is going to take I1.
Mm.
Right? Simple. Simple. See, I have not written exact Verilog code. Just written a piece of Verilog code. This itself will implement your mux. What you have done here, you have described your mux by using what? Its behavior, not by internal structure. You are not worried about internal structure. That is the advantage of RTL design. In RTL design, we describe any circuit or any design by its behavior, not by its internal structure. So generally, what the designers will do, entire bigger designs, what they will do, they will divide into different state machines. For example, you have everyone know I square C communication. Okay,
No, sir.
explain that only will take half an hour leave. Okay, ATM machine, right? Everyone know what is ATM machine.
Yes.
If I ask you to write the build a circuit for ATM machine by using gates, you cannot do. But if I ask you to describe the behavior, you can describe the behavior by using what? FSM, finite state machines. So first you should, bigger circuits, what you do? First divide into smaller finite state machine. Means divide into different states. So first state, I'll call it as first state, S naught state. This is called as reset state. In reset state, if card is not inserted means my sensor, the card sensor will be giving logic 0. Means card is not inserted. If card is inserted, the sensor will give what? Logic 1. If I am getting logic 0, then be in what state? Be in the reset state only. If I am getting logic 1, then go to what? Next state.
S1.
Next, this state will be generally some pin entering state. Pin enter. Now my user will enter the pin. Whatever the external input we apply, that will be converted to electrical signal through sensors. That embedded system engineer will take care. We are not worried. We worried only about the electrical signals what we get. This keyboard is also a sensor. The pressure what we apply on the keyboard, the pressure is converted to what? Electrical signal. So all those things are called as sensors. In ATM machine, I will type the pin. That is converted to electrical signals. The keyboard will take care. We are not worried. IC design engineers are not worried. So when pin entered is correct, go to next state. If pin entered is correct, in this state you have to evaluate whether the pin entered is correct. Then you will go to what? Next state. If pin entered is wrong, whatever pin he is entering, what? He is wrong. Or he is not entering the right pin. Then you go back to what state? Reset. Just I'm not describing the entire ATM machine, just I'm giving you the idea. So you have to evaluate here. Whatever pin he has entered, you have to compare with the internal database. If it is true, then go back to what state? Next state. If it is wrong, then go back to what state? Reset state. If pin entered is correct, then what you have to do? Amount entering state. If amount entered is correct, correct means one condition, amount should be greater than whatever amount he is entering, it should be lesser than it is balance. And he should enter the amount in proper denominations. He cannot enter, give me 433 rupees. ATM machine cannot be. It should be multiples of hundreds. So if amount entered is correct with proper denomination, then go to next state. Or if amount entered is more than is balance, or amount entered is not in proper denomination, then go back to what state? Reset state. Then my amount enter state will give logic 0 if amount entered is wrong, or amount enter state will give what? Logic 1. Then immediately I will go to what state? Next state. So in this state, I should produce a signal for the motors to count the nodes, and amount dispatch will happen. Amount dispatch. After amount, if amount is not dispatched, till that you be in what state? Amount dispatch state. If amount is dispatched, means logic 1, then go back to what state? Reset state. So this is the finite state machine. So bigger designs. See, I cannot give example of Ethernet protocol or something, right? I can give only general example. So bigger designs first write what? Finite state machine. And for each state, now you start writing the Verilog code. If card entered means you will not check whether card is entered or not. The signal will come from the sensor, right? From sensor will get the signal. Till the signal is coming. If the signal is coming, you will get logic 1. If the signal is not coming, you will get logic 0. So if the input is logic 0, you be in what state? Reset state. If the input is logic 1, then you go to what state? Pin enter state. In pin enter stage, you are waiting for pin entering. If pin entering is not happening for long time, like 2 minutes or 3 minutes, go back to reset state. If pin enter happens, then compare it for proper pin. If it is correct, then go back to next state by producing logic 1. So all these operations you have to write now. All the coding you have to do now for each state. So this is how you are going to write the RTL. So mainly what I can tell in RTL is why we go with RTL mainly is in RTL you can describe the circuit's behavior, not the internal structure of the circuit. I am not worried now whether this state is implemented by using AND gate, MUX or flip-flops. I am not worried. That my synthesis tool will take care. Now my only thing is I want to code this behavior of the finite state machine. I gave an example, right? If you have a MUX, correct? If you have a MUX, remembering its internal diagram is difficult, but remembering its behavior is very easy. So you can write the program for MUX. So for that reason, we use RTL design mainly. This is an example for what? MUX. Here we have done by it is what type of MUX it is? 4 is to
4 is to
4 is to
4
1.
is to 1.
Two select lines. Here we are using case statements. If select line is 0 0, output will take what? A. If select line is
A.
0 1, output will take what? B.
B.
Select line is 1 0, output will take C. Select line is 1 1, output will take what? D. Only remember this and write the Verilog code. That is what this case statement is doing. Sir, I am not knowing what is Verilog. Sir, I doesn't know what is layout. Don't worry, right? We have course. So our course is divided into two parts. First part is basics. Second part is advance. That I'll discuss in the next upcoming topics. What we cover in advance, what is covered in basics. Only in basics I'll mention what we cover. We cover Crystal, we cover CMOS, we cover Linux, we cover TCL, we cover GWIM. All those things we'll cover. So we will cover Distal, we will cover CMOS, we will cover Linux commands, tool command language, TCL, we will cover GWIM. GWIM is a text editor. Right? How to use the GWIM commands. All those basics we cover in basics of physical design. So if you are not knowing what is layout, then you will learn in basics of CMOS. We will do that because some universities may have this syllabus or may not have this syllabus, right? So we have incorporated what are the basics required. So this is the advantage of RTL. So RTL mainly we can write the code by using Verilog or VHDL. So we will describe the circuits based on its behavior rather than internal structure. We are not worried this MUX is implemented by using AND gate or gate, right? But just we are worried only its behavior. That is the main advantage of using Verilog or VHDL. So after writing the RTL code, see I am not going into RTL in very deep because the demo of that is done yesterday. Yesterday we had front end demo that's already covered what is present in RTL. So physical design engineers need not to be knowing RTL, but at least they should be having basic idea of how the Verilog code looks. If they know that basic idea, that is sufficient. So after RTL design, what is the next step? RTL verification. What is RTL verification? Verify this RTL design by applying what inputs? Okay. Apply the inputs here. First you apply one input. So how many? You have what? A, B, C, D, S not, S1. And what do you have? Y, right? If my S naught is 0, S1 is 0, S naught is 1, A is 0, B is 1, C is 0, D is 1. What is output Y? If it is 0, 1, right? What is output? Output is taking what? B. So what is B? 1. My output is 1. If my select line is 1 1 and my inputs are 1 0 1 0, what is the output? If
D.
S0 is 0, S1 is 0. If select lines are 0, my output is going to take what? D. Okay, S0 is 1 and S1 is 1. Sorry. If both are 1 1, my output is going to take what? D. What is present on D?
0.
0.
0.
Output become what? 0. So this is called as test case. This is called as what? Test case. Applying the set of inputs is called as what? Test case. Is any mistake I've done? 0. S1 is 0. Oh, I've written in reverse way, right? S1 is 0. Okay, this is S1 and this is S0. S0 is S0 is 1. S1 is 0. Output should take what? C. What is value of C? 0. Okay. Now it is correct. Okay, fine. So now I am applying set of inputs. Next I am verifying what is my output. If I get proper output, then my Verilog code is functioning properly, or else my Verilog code is not functioning properly. This is what we are going to test in the RTL verification. So next is RTL verification, or it's also called as design verification, or it's also called as functional verification. So all are same. In RTL verification, this is a program. This is a program which is going to apply different inputs. For select line, I'm applying different inputs. Right? I'm going to apply different inputs. So for the different inputs, I'll get what? Different waveforms. If I get proper waveform, proper output, then my RTL code is working properly, or else it's not working properly. But to become RTL verification engineer, see, RTL verification is not so easy. Don't think that is very easy, right? Just apply the inputs and check. Because for complex designs, RTL verification is very difficult. To become a RTL verification engineer, you should be knowing Verilog, you should be knowing system Verilog, you should be knowing UVM. What is UVM stands for? Yes, Universal
Universal
Verification
Verification Methodology.
Methodology. So all these things will form RTL verification. So even that course we have, and the demo is done yesterday. And if you are interested, you can ask for the video, demo video. Institute will provide a demo video for front end. So what is RTL verification? Apply the verify the functionality of a design. So if you want to discuss, right, please discuss with me. It is disturbing us. If you have any doubts, please ask with me. Verifying the functionality of a design by applying what different test cases. What is design here? Design is the RTL code what I have already written. This RTL code. This RTL code is what? Design. So this design is in what form now? Behavioral form. Verilog only it is in what form? Behavioral. So this we are testing by using RTL verification. After RTL verification, right? Next step is what? Synthesis. Now design is in behavioral form. That design your foundry cannot fabricate. Foundry requires what? In the layout form. So first, next what to do? You do synthesis. Synthesis will convert RTL to gate level netlist. It will not convert to layout level. It will convert to what level? Gate level, one step down. First convert to gate level. That gate level you convert to what? Layout level. Converting to gate level is done by synthesis. Converting to layout level is done by physical design engineers. So during synthesis, we convert RTL to gate level netlist. Or you can understand, for the time being, you can understand gate level diagram. Netlist, I'll tell later what is meaning of netlist. Now, what are the inputs for synthesis? If you want to do in synthesis, what are the inputs? RTL. RTL input is required, right? Whatever Verilog program you have written. Next, This RTL only you have to convert to the gate level description or gate level diagram. Then what gates you will use? Whether you can use mux, whether you can use half adder, whether you can use full adder, what you use? Who is going to tell that what you should use? What my tool should use? Synthesis you are not going to do, your tool will do. Only your role is to give this inputs. Right? So you have one more file which has standard cell information. That file is called as Liberty file, or it's also called as library file. This file mainly contains timing and power information of what? Standard cells. What do you mean by timing? Cell delay. How much delay your buffer takes, how much delay your inverter takes. What do you mean by power information? You have three types of power: leakage power, switching power, and short circuit power. If you are not aware, then it is discussed in CMOS basics without any doubt. So how much power each cell will consume? So this both information is present in which file? Liberty file for all the standard cells. Then what are standard cells? Some basic cells, right? Which is required to implement a circuit. Some of the examples of standard cells are buffer, inverter, OR gate, AND gate, NAND gate, NOR gate, XR. Some libraries even may have full adder, half adder, D flip flop, and mux. So only these things are liberty. For all these cells, you have cell delay, that is called as timing, and power information in this liberty file. So during synthesis, your tool will pick the cells only from this liberty files. It will not pick any other cells. Next, third file. What is the third file? SDC file. Synopsis design constraints file. It has timing constraints. Means your design should work with what clock frequency? Clock period, right? Mainly clock period. Uncertainty. Input delay, output delay. So all those things you'll understand when we do STA, static timing analysis. Means mainly, see, doing synthesis simply it is very easy, but do the synthesis to work with a clock frequency of 1 gigahertz. After doing synthesis, my design has to work with a clock frequency of what? 1 gigahertz. Then the problem comes. So that type of timing constraints we have in what? HDC file. So mainly we have clock period. So my design should work with this much clock period. 1 gigahertz means what is the time period? If your clock frequency is 1 gigahertz, then what is the time period? What is
1
the time
divided
period?
by
One nano,
1 gigahertz.
one nanosecond.
1 nanosecond, or it is
Nanosecond,
1000 picosecond.
picosecond.
So your design should work with this time period, 1 nanosecond time period. Whether that is working or not, how do you estimate? How do you evaluate? By doing setup and hold analysis. All those things you will understand later. What is that? So your design should work with 1 nanosecond time period. Your design should work with 1 nanosecond clock period. So that information you will give it in which file? HDC file. So you'll also learn how to write the HDC also. How you are going to learn, how you are going to write the HDC. You're going to learn that in this course. So see, you have plenty of commands in SDC. Few things I have mentioned: clock uncertainty, input delay, output delay. So all those things we'll understand. So when we do SDC or STA, static timing analysis. So these three files are mainly important for synthesis. Then what is output of synthesis? Gate level netlist. Output of synthesis is gate level netlist. Even gate level netlist is also a Verilog code. Here RTL is Verilog means even gate level netlist is also a Verilog code. And what is the difference in between both? See, in RTL code, this main interview question, right? What is difference between RTL and gate level netlist? In RTL, you can have any syntax of Verilog. You can use assign statements. You can use case statement. You can use if statements. You can use procedural blocks. Anything can be used. But in the gate level netlist, you should be having only gate and its connections. You cannot be having if statement. You cannot be having assign statements. You should not have any case statements. Only gate and its connections. So example, right? You have example here. One example. If you look into this. Here you have two blocks. This is first block. Here you have plenty of blocks, correct? Your one chip has how many blocks? Plenty of blocks. All these blocks, each person will write Verilog code for each block. And RTL integration team will integrate all the blocks. So the same example I have taken here. This is one block. Right? This is one block. Just a simple block I have taken. This is one block. For this block, we have done the synthesis. This is another block. For this block also we have done what? Synthesis. And RTL engineer, see this RTL one engineer has written. This RTL one engineer has written. So combining both RTL is done by RTL integration team. That is done in RTL stage itself. At that stage itself they will do. After synthesizing, I'll get like this. For two blocks, in one block I have this cells, in another block I have what? These cells. Then what is netlist? If you take only one block, right? You take only one block. This is a one block. Now you take only one block. This block you take. For this block, what are the inputs? ABC is the input for entire chip. I am talking about only one block. What are the inputs? M, N.
N.
Yeah.
What is the output? P is out. Only for this block, now I have Verilog code. So what is the Verilog code present here, right? So first is module name. See, module name can be anything. You can give any module name. And here you have ports declaration. See, inputs and outputs of a block is called as what? Ports. But input and output of a cell is called as what? Pins. You have first cell. What is the first cell name? And 2. It has input. What is the input of that? A. Another input is what? B. Output is Y. So A, B, Y is called as what? Pins. But M, N, O, P are called as what? Ports. Inputs and outputs of a block is called as ports. Input and outputs of a cell is called as what? Pins. So first we are declaring ports for this entire block. What are the ports I have? M, N, O are the input ports. What is the output port? P. So I am declaring in next. I am declaring what are the inputs? M, N, and O. What is the output port? P. Next, intermediate signals I have anything, right? This intermediate signal I have N1 and N2. So these intermediate signals I am representing it as what? Wire. So intermediate signals we have to represent by using what? wire. Next, first cell. What is the first cell I have? This AND 2. This AND
And
2 is a name of a AND gate present in library file. Liberty file. I already told you, right? One of the input is what? First input is RTL, second input is Liberty file. So this AND 2 is a name of AND gate present in which file? Liberty file. Same name I should use. So I am using AND 2. Next, instance name U1. This instance name is given by synthesis tool. So synthesis tool will give separate instance name for each cell. Because in my design I can have hundreds of AND gate. From one AND gate to another AND gate, I should be having some difference. So one first AND gate will be having U1, second AND gate will be having what? U2. So for every cell, my synthesis tool will give instance name. What's the instance name for this gate? U1. You are not going to do it, but synthesis tool will do it. So synthesis tool generally it will take U1 only. If you are writing, you can take any alphabet. It's no issues. Next is port mapping. This is called as what? Port mapping. So A pin, where it is connecting? M. It's connecting to M. So dot A of what? M. You can see that. Next
Okay.
B pin, where it's connecting? N. B is
Yeah.
connecting to N. Dot B of N means B is connecting to N. Then Y. Y where it is connecting? Y is connecting. Y pin is connecting to what? Net? N1. So what is your doubt?
And
That is a normal syntax. Syntax of Verilog. So for this pin, if you are connecting M, then we have to maintain dot only. That is syntax of Verilog. Then only we can understand. See, or else if I mention A of M, right, then it is like A of 0, something like this. So I'm mentioning my A pin is connecting to this O. Then I should mention what? Dot in front of that. So dot Y means my Y pin. Y pin is connecting to what net? N1 net. That is shown here. So first cell information is done, right? So A is connecting to what? Port M. B is connecting to what? Port N. Y is connecting output of cell, output pin of this cell Y is connecting to what net? N1 net that you're
N1.
seeing. Next cell. What is the next cell? R.
What?
What is the instance name? U2.
U2.
So where this A pin is connecting, this A pin is connecting to net N1. So that
N1.
information you're seeing here. So B is connecting to port O that you are
Port
seeing
O.
here. And Y is connecting to net N2 that you are seeing
N2.
here. At last you have what? Inverter. So inverter A pin is connecting to what? N2 and B is connecting to port P. The same
P.
thing you are seeing. So this is called as gate level diagram. This is called as what? Gate level netlist. So in this gate level netlist, if you see, right, you are seeing only gate and its connections. You are not seeing any if statements, case statements, or any assign statements. What do you mean by assign statement? So in Verilog, you will use like this, right? Assign A is equal to B. You should not see any assign statements like this. Only you should see gates. You are seeing only gates here, correct? Only gates. And it's saying connection between gates, correct? Whether you can see connection between gates in the Verilog code, you can find, right? Because Y is what? Output pin of what? AND gate is connecting to what net? N1 net.
N1.
N1.
A is what? A is input pin of what? OR gate. It's connecting to what net? N1 net. It's
N1.
clearly
N1.
indicated output of AND gate is connecting to what? Input of OR gate. Connection is seen.
R gate.
Similarly
Sir,
here,
sir, once again, can you tell me why the dot exactly is used?
that is the syntax of Verilog. If you simply
Okay.
write A of M, right?
Ah.
It can be normal representation also. Normal variable you can represent like this. Dot A of M, A of 0,
Oh,
A of 1.
okay.
You can also represent like this.
Okay. Okay.
But this is not a normal variable, right? It is a meaning that A pin is
Will
connecting O port or net. So
okay.
to represent this, we have this syntax.
Okay. Thank you.
So here also you can see any doubts, any problem here. So here also we have output of this OR gate Y pin is connecting to what net? N2 net. And
And
again input of input is connecting to what net? N2 net. So both are having what? Connections. So that is what I mentioned, right? Netlist means it has gate and its connections. That is what you should see. This is what first block. What is for second block? Just I have taken second block, right? Second block has how many cells? Just I have taken 2 cells. But in the real design, each block you will see minimum 20 lakhs to 30 lakh cells in real physical design.
okay.
It may also have 1 lakh or 50,000. The cell count will range from 50,000 to 30 lakhs. Any count you may have. That depends the complexity. So minimum is 50,000.
Okay.
Rare case you will find below 50,000. So here in a block, how much I am seeing? How many cells I am seeing here? 3 cells. So you will get a file with 20 lakh cells. That is the difference, right? That is what the main difference. So here I have one more block. For this one more block also I have Verilog code, and I need not to explain this, right? For this block, what is the input? Q is the input.
You
One more input is what? R.
are
So instead of representing here, we have represented here. What is one more output? Yes. So
yes.
AND gate is connecting to what? Q and B is connecting to R. You can see that connection here. A is connecting to Q and B is connecting to what? R, and Y is connecting to net N1. And in
And
A is connecting to net N1 and Y is connecting to port S. That you can see. That Verilog code. This Verilog code is for this block. This Verilog code is for this block, and this Verilog code is for this block. And what is the connection between them? Connection between them is done by top module. Right? So how this connection between, so this is for one block, this is for second block. Now we are writing the Verilog code for entire chip. This entire chip, right? This complete thing is entire chip. For entire chip, what is the input? A, B, C. What is the output? Y.
I
So now I have to write the program for entire chip. This is the article code for entire chip. What is the entire chip name? Top. What are the inputs for entire chip? A, B, C. I am showing only 3 ports. Generally, you will be having thousands of ports. So inputs are A, B, C. Output is what? Y. That is declared. So intermediate, I have what? One net. Now I am calling these two modules. Means my top module is integration of what? Two modules. What is that first module? Temp1. Temp1 is present here. What is second module? Temp2. So for temp1 M pin, the temp1 M port, what is connected? A is connected. That is what I am mentioning here. For temp1 N, what is connected? B. That is what I mentioned here. For O, what is connected? C. Out of O of C. What is the output of this block? What is it? P. So P is connecting to what net? N1 net. That is what I mentioned here. Next, we are calling what? Second module, temp2. What is how this from this inputs, how the output is generated, that is present here. That we are not bothered while letting the chip top. So this top module is calling the first module. So for first module, I have program here. It's like a function in C, right? Everyone know. Second one is second block. I'm calling second block. Second block input is what? Q. Q is connecting to what net? N1 net. R. R is connecting to what net? N2 net. Where is N2 net? R is connecting to N2 net, but N2 net is not shown. No, that should connect to one net. I think that net is missing in this diagram. Okay, net is not at all declared. Okay, we assume that N is, see, for example, we assume that so for R, it will get the output from some other block. So that net I have to mention, but that is not mentioned here. That is missing here. And output S is connecting to what net? Y, right? So top module is calling first block and second block. So I have only two blocks here, but generally we'll be having 40 to 50 blocks. All the 40 to 50 blocks you can see here in the full chip level design, right? Now this is called as synthesis. This is called as netlist. So in the netlist you are seeing what? Only cells and its connections. In the top module you are seeing only blocks and its connections. How the connection is happening between blocks. So P is connecting, right? P is connecting to N1 net and Q is also connecting to what? N1. The meaning is what? Output of temp1 block is going to what? Temp2 block. So this is the output of synthesis. Now design is in what form? Yes, design is in what form now? Yes, design is in gate level form. So even this gate level form, my foundry cannot fabricate. For foundry should be fabricate, then what is required? We have to convert this into GDS form. So now our role of physical design engineers is convert this gate level description into GDS form. So before going to the physical design, there is one more team coming into picture, that is called as DFT team. DFT stands for what? Design for testability. So what DFT team will do? So DFT team will add some additional logics in the design. Additional cells they will add in the design without affecting the functionality. It will not disturb the function. Carefully they will add some additional cells in the design so that we can easily test the chip after fabrication. See, testing the chip happens after what? Fabrication. So how to test the chip? Pass the inputs, pass some test case inside, right? Apply logic 1 and pass inside. Between flip-flops you pass what? Logic 1 and check what output you are getting. So for example, you assume that you have D flip-flop here. You apply logic 1. So D flip-flop is having Q pin and it's connecting to SI pin. Q pin, it's connecting to what? SI pin and Q pin. See, I will not go into DFT in depth because DFT is again a separate course. Right? So I think the DFT demo will happen. So you can go with the DFT demo again, right? Because it is a separate course. I will just explain what is DFT. So if you apply logic 1 here, after one clock pulse, this logic 1 will come here. After second clock pulse, this logic 1 will come here. This after third clock pulse, this logic 1 will come here. I applied logic 1 and output is also I am getting what? Logic 1. If anything is happened in between during fabrication. If this net is not formed only, there is a breakage of net. This net is broken down. During fabrication, we are not assuring, our foundry is not assuring your chip is fabricated clean. Out of 100 chips, 30 chips are thrown away. Only 70 chips are used because 30 chips has some issues, fabrication issues. So here the net is broken away. So obviously, if I apply logic 1, the logic 1 will not come here. I will be seeing high impedance state here because net is broken away, right? This logic 1 will not come out. So I applied logic 1, but the logic 1 is not coming out in the chip. Then I can assume that in this path there is some problem. So in the path of flip-flop, right, there is some issues or problems. See, I am not understanding. See, this is a PD demo. This is a PD demo. What is your name? VSK, right? You are asking some question, right? This is a PD demo. PD demo session. You are joining for which class? PD demo only, right? You are joining for PD demo only, correct? Okay. So I have applied logic 1. My logic 1 should come out. If I apply logic 0 here, the same after first clock pulse 0 will should come out. After second clock pulse 0 will come out. After third clock pulse 0 will come out here. If any breakage has happened in between, then this 0 will not come out. Or for example, some VDD has shortened here. VDD while passing some net, right? See, the short will happen easily. After fabrication, my metals are not fabricated properly. They are fabricated like this. I can see metals fabricated like this. Because here etching happens through chemical mechanical polishing, means chemically you will remove the metal layers. So metal layers cannot be flat like this. They may be like this. So without our notice, it has shorted here. Foundry cannot find where is the short. They cannot use battery and they cannot find where is the short. Only they can validate whether short has happened or not by passing what? By passing the inputs to the chip. So while if I pass the input to the chip and here some other net is passing and short has happened in between, this net is VDD net. So VDD has shorted. If I apply logic 0 here, always I will be getting what? Logic 1 here, right? I will be always getting logic 1 here because here what is connected? 1 is already connected. Logic 1 is connected. Even the 0 is coming, 0 is not taken because the short has happened. Nearby net which is passing, this is VDD, this is normal net. This net is this net. This is VDD net. So VDD has shorted to this. So this net is always showing VDD only. At output side, even though I'm applying logic 0 as input, output I'll get always what? VDD. VDD means what? Logic 1. Means the meaning is somewhere in between short has happened, then throw the chip. So to test this chip like this, so DFT team will do some modification in our netlist. Alright? They'll do some modification in our netlist to test this chip. To make testing easy, they'll do some modification in the chip. That is called a scan chain insertion, MWIST, built-in self-test, ATPG, automatic test pattern generation. See, all these concepts you can learn in DFT, how to do all these things. But what is role of DFT? Role of DFT is modify the netlist. They will do modification in software only. Modify the netlist so that the modified netlist, once we do physical design, and after physical design we will send what? GDS file to foundry. After fabricating chip, we can test the chip easily. Modify the netlist so that testing becomes very easy. So that is the role of DFT. So DFT will do scan chain insertion. So they will do ATPG, automatic test pattern generation. They will do built-in self-test. So all these concepts will come in DFT. So you can learn in DFT. That is separate course. So DFT is not part of physical design. In physical design, you learn synthesis, but not DFT, because DFT in industry also it is a separate person will do DFT. Only we have separate engineers called as what DFT engineers. They will not learn synthesis. They will not learn physical design, but they will learn the concept what I told. What are the concept I told? ATPG, automatic test pattern generation, built-in self-test. Scan chain insertion, all these concepts they will learn. So they will learn scan chain insertion, ATPG, built-in self-test, right? So all these things they will do so that my chip can be tested easily after fabrication. So to facilitate that, the DFT team will work. So what the DFT team role is, they will modify this netlist. Right? This netlist will not get directly. They little bit modify the netlist. In between, they'll add some flip flops. What is it? What is the role of if I add one flip flop here? Anything happens? What is role of flip flop? What is on D pin directly pass to what? Q pin. That is called a scan chain insertion. Not exactly the same. Little bit almost same, right? So they will do scan chain insertion. That is inserting the flip flops wherever they require at the test points. So that is what the DFT team will do. They'll modify a little bit netlist. After netlist is modified, then that netlist will come to what? Netlist modification means what? One or two cells are added in between. Modules, this blocks, top level block, everything remains same. Only one or cells added in between. That is what the modification they will do. After modification, right? Then we'll start with what? Physical design. So now we'll start with physical design. We will take a break. After 15 minutes break, we'll take. After the break, we'll see what happens in physical design. Right? What we do in physical design. Right? So first step in physical design is what? Partitioning. So we'll start from here. And after discussing what happens in what is physical design, next we'll discuss physical design completes floor plan everything. Then next we'll discuss what is our syllabus content. Next we'll discuss about course content. Next we'll discuss about placements. Then we'll wind up. So next we have session for next 1.5 hours. Right? So we'll meet after 10 minutes break. So now the time is 10:55. We'll join again at 11:05. Take a break and come. So now physical design, right? So what the physical design will do? Converts gate level design into physical layout form, right? Now input of physical design is what? Netlist file, but output is GDS2 file. So this is one of the diagram which shows physical design. You're not understanding anything, right? On this diagram, nothing is visible. So here you can see one small cell, right? And that cell is having the layout. So physical design. So now we'll see what happens in physical design. Now you're not understanding anything. Sangmesh, I think you have joined late, or I don't know why you're asking this question, because till now I have explained the same thing, right? Netlist. You joined late, Sangmesh? Yes, right. Please go to the videos, because I have done the elaborated explanation on the netlist itself. So request for the recorded video from the institute, right? They will give you the recorded video. You don't have to pay for anything. They will give the demo video, recorded video, this video, and I have done the elaborated explanation on the netlist. Please go through that. So netlist is nothing but it's also Verilog code, but it has only gate and
connections.
it's output of a synthesis. So output of synthesis, this netlist will go to what? It will go to DFT. DFT will do some modification in the netlist so that chip can be easily testable after fabrication. Next is physical design. In physical design, whatever gates we have, right, we have to convert into what form? Layout form. See, we are not going to write the layout for each gate. I'm not going to write. Physical design engineer is not going to write, because we will not be having one gate or two gates. We will be having millions of gates. Here you can see only three gates. In each block, you are seeing three gates, but in real design, in each block, you will be having 10. You may have 10 lakhs gate. You cannot write the layout of 10 lakhs gates. Layout of each gate, like AND gate, OR gate, like each basic gates, layout is already drawn from the layout team. You are not going to draw the layout. Layout is already drawn from the layout team. The layout you will use it in your design. They'll use it in a file. they'll give you the LEF file, layout exchange format or library exchange format. We will discuss that. What are the inputs for physical design? Everything we'll discuss in the physical design course in detail. So we will get this file from the layout team. This LEF file, layout exchange format, has layout of all the cells, standard cells, what I mentioned earlier, right? This for all these cells, we have layout in the LEF file, so we will use that file. So we are not going to write the layout. Then what we will do? So first step in physical design is partitioning. Entire chip is divided into different blocks. This A is called as one block. Right? This A is called as what? One block. B is called as another block. C is third block. D is fourth block. E is F is fifth block. C is what? Sixth block. So entire chip is divided into number of blocks. Generally, we divide it into 30 to 40 blocks. A single chip is divided into what? 30 to 40 blocks. A full chip may have a cells count around 30 million. What is 1 million stands for? 30 million means 3 crores. A full chip may have a cell count in the range of 3 crores. So we cannot do physical design for 3 crores cell count. Tool will not handle it because we have RAM capacity, right? Tool should handle the RAM. So tool cannot handle for 3 crore cells. So we cannot do physical design. My tool will crash out. So if you want to do physical design, then we can do maximum 40 to 50 lakh cells, not more than that. So for the design, what we do, we divide this entire full chip into what? Different blocks. Then we'll do full physical design for each block. Then we'll integrate all the blocks. Then we'll create the GDS. So this blocks, why they are not in a square shape? We can divide the chip in the square shape, right? This itself is very tedious. It's not very easy to divide a full chip into different blocks. I can divide like this. Why I have divided like this? It is not area wise division. It is a module wise division. Module wise means what? Or block wise division, right? See this full chip, whatever I discussed earlier. If you see this full chip, this full chip has how many blocks? In first block, how many cells I have? In second block, I have
Three,
what?
sir.
Two
Two.
cells. So this requires more area and this requires what? Less area. Because this has only 3 cells and this has what? 4 cells. So here, first block is A block. You assume second block is what? B block. So A block requires more area and B block requires what? Less area.
Yes, sir.
So here splitting happens based on the module. This entire module is one block. This entire module is called as what? One block. In this module, in this block, how many cells I have? 1, 2, 3. In this block, how many cells I have? Only 2.
Two.
So here splitting happens based on the number of entire module should be given to one block. It's not an area wise splitting. So for that reason, one block may have more area, one block may have what? Less area. If you compare to A, F is having what? Very less area. So most critical block is given to the person who is senior and less critical block is given to the recently joined freshers or with 2 years or 3 years of experience. Now, what happens in physical design? Now, doing partitioning, handling the full chip is done by full chip level engineers or chip tops. They are also physical design engineers. When you have experience, right? When you have experience of 7 years, 8 years, then you will be moved to what? Full chip. So till 5 to 6 years, you will be working with what? Block level. See, we don't want more resource in full chip. Hardly in one project. 4 persons in full chip is sufficient. But for one full chip is divided into how many blocks? Almost 40 to 80 blocks. We want more block level engineers. Now I want to do physical design of what we will do. For one engineer, I'll assign A block. For second engineer, I'll assign what? B block. The third engineer, I'll assign E block. So each block is assigned to each engineer. See how my full chip engineer came to know that I should assign this much area to each block. Whether it is assigned blindly? No. He has to check how many cells he has in each netlist. If you see the netlist, right? How many cells he has? How many cells he has? 3 cells. What is the area of each cell? He has to calculate. Area of this AND gate is, for example, you assume it is 5 micrometer square. This is 5 micrometer square. Inverter is 2 micrometer square. How much area you require? 12 micrometer. So total area required is 12 micrometer square. But you cannot use only 12 micrometer. Some extra space is also required. Instead of 12, he will give you 16. Some extra space is also required later. You may add some additional buffers to your design. So he should create this area in such a way that you should occupy all these cells. The entire cell layout should be occupied. The area of each block cannot be less than the area of cells. It should be more than the area of all the cells. Even it cannot be equal. It should be obviously more than the area of all the cells in each block. Okay, please tell me. Shape. That is what the talent of full chip level engineer. He has given this much block. He has given this much size of chip, and he knows each block requires some area, right? Some area each block requires. He has to adjust in this. While doing adjustment, automatically shapes will come. He has to adjust, right? Everything he has to adjust. So while doing adjustment, one will take L shape. So one, okay, this is square shape. This is square shape. This is square shape. So one block somehow I have to adjust here. What I'll do? Okay, this I'll make some L shape. This I'll make some L shape. This last block I'll somewhere adjust here. This some free space I got it. I'll add one more block. So instead of using rectangle shape, if I use some L shape, right, some small block I can adjust in between. So like that, for that reason, see, all the blocks will not be having this type of shapes. Just we have written to show you, even you can have this type of shapes. All the blocks will be not having this type of shapes. Most of the blocks will be in rectangle shape. Only few blocks may have this type of shapes. Inverted L shape, or D is having this type of shape, right? All the shapes are possible during partitioning. So that is the role of full chip level design engineer. You will be becoming full chip level design engineer when you have experience. Now, then what is the role? So now every engineer who joins to a company, they will work on the block level design. They'll work on what? Block level design. So in the block level design, so each engineer will do the physical design of each block. For each engineer, what is given? Their netlist is given. So for this block level, this netlist is given. For this block engineer, this netlist is given. For them, their own netlist is given. So by taking their own netlist, they'll start doing the physical design. Right? The shape is this shape only. The shape is given by the full chip. Now, when we want to do block level physical design, these are the steps: floor planning, placement, clock tree synthesis, routing, and sign off checks. Each block level physical design engineer will do all these things. So what is the first step? Floor planning. So floor planning has these 4 major steps. What is the first step? Create core area and die area. So here block shape is, here if you see the block shape is what? Rectangle. So even we may have block shape, as we already told, even we may have block shape as like this. So instead of drawing here, draw somewhere here. Even this type of block shape is also possible. This is one block shape. So this is core area and outside portion is called as what? Die area. It's not die area. General word is die area, but it's called as what? Block boundary. Inside one is core area, outside one is called as what? Block boundary, but a general name is called as what? Die area. So die area is used only for full chip. Full chip also has these type of things, right? For full chip, if you see, this is called as what? Core area. This is called as what? Die area. In full chip, it is called as die area. For each block, you will create again this type of structure. Inside one is called as what? Core area for the block also, but outside one is called as, generally everyone term it as die area, but it is not a die area, it is called as what? Block boundary. Block boundary. In full chip level, it's called as what? Die area, but at the block level, it's called as block.
Boundary.
So first you have to create this. So what is the next step? Next step, port placement. See, port placement means inputs and outputs of your block, right? What is the input and outputs of this block? First block, M and O. What is output? P. That is present in netlist. In netlist, I have in the logical form. Logical form is in only the text form. M, N, and O. And what is the output? P. Logical form means it is in the form of what? Text. Now I have to convert into form of physical. Physical means convert to the form of metal layers. So M, N, O, right? M, N, O. What is this? This is a piece of metal layer. So the next step is what? Port placement. What is port placement? Place the ports in between core area and die area. All these ports you place. What are ports? Ports are input and outputs of a block. So here these are metal layers, piece of metal layers. So in this example, if you take this is M. So for M, I'll create a piece of metal layer. For N, I'll create a piece of metal layer. For O, I'll create a piece of metal layer. In this block, I have only 3 ports, but in the real design, we'll be having what? Plenty of ports. So all these are piece of metal layers. So how to place these ports? What is the guidelines for placing the ports? So everything we will discuss in advanced physical design. So whether the block level design engineer can blindly place the ports? No, he has to clearly see the connection. For example, all the outputs of block A is going to the inputs of block B. Then all the output ports should be placed here, right? All the outputs of block BA is going to inputs of what? Block B. See, here I have not drawn core area and die area. Right? Here there is no core area and die area. We are not shown. But here also actually there will be core area and die area. We are not shown that. So all the output ports I have to place here. For block A, all the inputs are coming from what? Block C. Then all the input ports should be placed here. So directly output ports of block C should be present here. So output ports of block C should be present here. Input ports of block A should be present here. So directly we can make a connections. how they are interacting with the neighboring blocks. So based on that, we have to do the port placement, where we have to place the ports. It's not that I feel I want to place input ports on the left hand side, right? So I'll place on left hand side. I feel to place output port on the right hand side, I'll place right hand. It's not like that. We have to see how my ports are interacting with neighboring blocks. So based on that, we have to decide which side we have to place the ports. That is, see, everything is not so easy how I draw. We have many guidelines to do. All those things we'll discuss in advanced physical design. So what is our next step? Next step is, see, I'm only discussing the major steps, not all detailed steps. All right. Next step is what? Macro placement. So all these are macro. What are macros? So in see, apart from standard cells, we also have few layouts which are already designed and tested. It's like your puliyogre powder, rasam powder, or sambar powder. If your mother or if you are cooking, right, you will cook everything from the scratch. If puliyogre powder is readily available in the market and you are not sure that you will get the same taste of that, then you will directly purchase from there and mix it with the rice. If it's readily available in the market, why you will prepare from the scratch? Similarly, few circuits which are readily available in the market, not in the market, few circuits we already have, few layouts we already have. For example, SRAM. For SRAM, layout is already there. Why I have to write the Verilog code for SRAM? So why I have to implement SRAM by using what? Basic gates. Why I have to use those basic gates here? Already I have layout of SRAM. In the previous project, I already have layout of SRAM. It's already done. I want on 5 SRAMs in my design. Directly you use layout of SRAM, right? So SRAM, now this SRAM is not a small design. It is what? It is a complex design. It's not a standard cell. It's a complex design, which is already designed and tested. And we feel that this is best. Then directly reuse it. What happens? My cell count has reduced, right? Each SRAM will result in 10,000 cells, we assume. For each SRAM, if I write the Verilog code and if I implement here, how many cells I'll get for 5 SRAMs? 50,000 cells. Instead of writing Verilog code, instead of doing synthesis, if I directly use the layout of SRAM, then what is the advantage? Almost 50,000 cell count I have reduced. What is present inside the SRAM, we are not worrying. We are blindly believing inside the SRAM I have the best layout. That is what I have given the example of puliyogre powder. What they have used in puliyogre powder, we are not worried. Our role is only mix it with the rice. Here also our role is connect with this SRAM to the standard cells layout. Standard cells are placed. Standard cells are placed means standard cells layout are placed only after placement stage, during placement stage. But during floor plan stage, if we have any macros, we are going to place it. What are macros? Macros are complex designs which are already optimized and tested. That which is available, we cannot use. We have MTR, GRB, some other thing, right? We will not use everything. We will use only which is best. So we can tell which is already optimized and tested. Right? So all these SRAMs macro I am using. Not only SRAM, right? Only also PLL, phase lock loop. For phase lock loop, I cannot write the Verilog code because phase lock loop is analog circuit. For analog circuits, what are analog circuits? We can write Verilog code only for digital circuits, means the circuit which is working with logic 0 and logic 1.
One.
Sometimes in my design, I also require analog circuits like PLL. What is role of PLL? It is going to produce clocks, different clocks. It will take clock from crystal oscillator. Crystal oscillator is producing some clock like 333 megahertz, but my design requires 500 megahertz clock. To convert from 333 megahertz to 500 megahertz, I require what? PLL. But PLL I cannot write the Verilog code because PLL is an analog circuit. PLL will work with time changing signal. I am not going to explain what is content of PLL, like voltage controlled oscillator, differential amplifier. I'm not going to explain that. You can go through the content of PLL in any way, any of the websites, right? But PLL is an analog circuit. We cannot write the Verilog code. Then how did I get the PLL layout? This is done by layout team. Layout team is drawn the layout for complex PLL, and directly we are reusing the PLL layout. So all these are called as macros. So first we have to do macro placement. Why? Because macros are few in numbers. See, in a block, if I have 5 lakh cells, 5 lakh standard cells, I will be having macro count ranging from 10 to 100. Only within 100. Macro count will not be generally it will not be more than 100. Sometimes we may see 300 to 400, but generally it will be within 100. Majoritarily, we will see within 20, but in few cases even we'll see 40, 50, 60, 70, 80, 100 also we can see. So as compared to the standard cell count, the macro count is very less. So first we'll do macro placements. Macro placement plays very crucial role in physical design. So there are many guidelines for macro placement. So we will see what are the guidelines for macro placement, how to do the macro placement. All right. If macro placement is not done properly, what happens? Right. All those things we will discuss in the theory part, theory sessions, and we also show in the lab part. So next step of physical design is macro placement. After macro placement, we have what? Power planning. So
Power
plan the.
planning.
So we will create the stripes like this using metal layers. VDD, VSS, VDD, VSS. Stripes I will create VDD, VSS. So why we will create the stripes? Why we have to do power planning? Why we have to do power planning? Can anyone answer? Because every cell, if you see the layout, right, every cell requires VDD and VSS connection. Inside the cell layout, if you see, it requires what? Every cell requires, this is VDD and this is what? VSS. This is a layout of cell. Every cell requires VDD and VSS connection. If I have 5 lakh cells, all 5 lakh cells requires VDD and VSS connection. I have to plan the power. Power should reach to a cell without IR drop. What is IR drop? For example, you assume that I have one VDD port here. This VDD port. I have one cell here. I have not done any power planning. Just I am connecting this VDD here and VSS I am connecting here. So this cell will draw the current, right? The current will flow through what? Metal layer. And this metal layer is having what? Resistance. So this metal layer is conducting current. It also has what? Resistance. So I into R will result in what? Voltage drop on metal layer. This is the cell. For this cell, we are making a connection. For VDD, we are making connection through metal layer. For VSS, we are making connection to metal layer. As when this cell is drawing current from VDD, the current and resistance is going to create what? Voltage drop. If this VDD is 1.5 volts, so in the physical design, we will be having voltage range in the range of 1.5 or 2 volts only, not in like your textbooks 5 volts or 12 volts. Right? If VDD is 1.5 volts, only 1.2 volts will reach here. What happens to remaining 0.3 volts? It is dropped on the metal layer. 0.3 volt is lost on the metal layer. And this 0.3 volts is converted in form of what? Heat. My VDD is 1.5 volt, but how much voltage is reaching for my cell? What is the reason? Reason is resistance, right? Resistance is more. If I reduce this resistance, I into R, the product will come down. This value may also come down. So for that reason, properly plan the power for your block so that you are going to minimize this IR drop. Every cell will get almost same VDD voltage, right? This is 1.5 volts, even this is also 1.5 volt. Instead of 1.5 volt, see VDD means positive voltage, 1.5 volts. VSS means ground, right? Ground voltage, 0 volts. So because here there is no negative voltage, because I already told you ASIC design flow can be done only for digital designs. PLL, only PLL is analog circuit. Only for PLL we'll give some analog voltage separately. That we have to plan. If we have PLL in our block, every block will not be having PLL. Any block is having PLL, we have to separately plan for the supply voltage for PLL. Apart from PLL, all other cells requires what connection? VDD and VSS connection. VSS means 0 volts, VDD means positive voltage. It's not always 1.5 volts, it depends upon the chip. What is the operating voltage of your chip? So output out of 1.5 volts, only 1.2 volt is reaching to the cell. 0.3 voltage is dropping out on the metal layer. This process is called as what? IR drop. Because of IR drop, what happens? Cell delay will increase. And sometimes cell may not work properly also. So for that reason, we have to reduce the IR drop. See, IR drop is happening by small amount, it's okay. Like this is 1.5, but here I am getting 1.49999. That is okay. Or 1.499. That is okay. 1.498 is okay. But 1.48 is not okay. So because millivolt is also very important. That may change the characteristics of the cell, right? So we have to reduce this IR drop. To reduce this IR drop, how to do the power planning? How to properly plan the power so that every cell is getting VDD and VSS without IR drop. That is what we do it in what? Power planning. So you will understand when we start doing the labs, when we start doing physical design, you'll understand how we do power planning. We'll create stripes, we'll create rails, and these stripes will connect to the rails, and rails will connect to standard cells. So all those things you will see during the power planning. So these are the major steps in floor planning. So you also have some minor steps like physical cell placements. So all those things we have explored because all those things requires a lot of explanation. We cannot cover in 3 hours demo, right? All those, even those things is covered during our course. Physical cell placement, even that is done in floor planning, like tap cell placement, handicap cell placement. So why tap cells? To avoid latch-up problem. So all those things requires a lot of explanation. So we are excluding as part of now. So after floor planning, so these are the major steps of floor planning. After floor planning, what is the next step? Placement. What is placement? Place all the standard cells inside the core area. What you are placing? Layout of cells. You know your block requires what layout, what cells you block your block has. Right? Your block has what? AND gate, OR gate, inverter. So
Okay.
take the layout of these blocks. So layout is given from the layout team. Take the layout of these blocks and place this layout inside the core area. All these are layout of the blocks. Yes, any doubts? One student was asking in online. Any doubts you have? See, why they are called as standard cells? Why these cells are called as standard cells? Because layout of this cell, if you see, right, almost they have what, same height. Yeah, every cell layout, if you see, they have what, same height, but width will be different. I'm talking about the layout. So you can see here also, right? In this PPT also you can see every cell is having what, almost same height.
Height.
So this height of this cell, height of this cell is almost same. This cell height, this cell height is almost same. So every cell is having same height. But width is what, different, right? This cell is having very small width, this cell is having what, more width. So place all the cells. So this is called as placement. This diagram you can see, right? This is placement. First my tool will roughly place. In rough placement, all cells are overlapping each other. Then my tool will refine the placement. It will do detailed placement so that my tool will place cells very neat without overlapping. They can touch each other, but they should not overlap. Touching means just they can edge to edge, it can touch, but they cannot overlap. So without overlapping, all the cells are placed inside the core area. All the cells means it is what, layout of cells. That is called as placement. After placement, what is the next step? So clock tree synthesis. So build a clock tree. So why we have to build a clock tree? If you see this diagram, you'll understand. What happens if you don't build a clock tree? So you can see this diagram, right? See, earlier if we see one clock port in our design is connecting to what? It's connecting to all the flip-flops. You can see here, one clock port is connecting to what? All the flip-flops. Clock port means what? It's going to produce a clock. That's connecting to all the flip-flops. For that reason, what happens? The load capacitance here will increase. Load on the clock port will increase. This load capacitance is nothing but what? Net capacitance. Net capacitance means what? Metal capacitance. The metal layer what we used to connect, right? This metal layer has what? Capacitance with respect to ground. It has capacitance with respect to what? Ground. That is called as net capacitance. What is net capacitance? Capacitance of a metal layer with respect to ground is called as what? Net capacitance. So I have one metal layer connecting to this flip-flop. The net capacitance of this is 1 Fermi farad. Again, this I am counting. What is the net capacitance? 1 Fermi farad. Again, I am counting here. What is the net capacitance? 1 Fermi farad. Again, I am counting here. What is the net capacitance? 1 Fermi farad. Sum of all this net capacitance is going to form what? Load capacitance. That is called as what? CL. That is going to form the load on clock port. This load capacitance we are not connecting. Automatically is going to form because of what? Sum of all this capacitance. So here this load capacitance is two parameters. One is net capacitance plus pin capacitance. This net capacitance because of metal layer. Metal layer. What pin capacitance means? At the input of every cell, you have pin capacitance. This pin capacitance plus net capacitance is going to form what? Load capacitance. So now, if I have 1000 flip-flops, net capacitance is 1 Fermi farad. We assume net capacitance is 1 Fermi farad. Pin capacitance is 1 Fermi farad. So totally how much? 2. If I have 1000 flip-flops, then what is the total CL? CL is having 2000, right? Because for one cell, pin capacitance is 1 Fermi farad. Net capacitance is how much? 1 Fermi farad. Total it is what? 2 cell for one cell. If I have 1000 cells, 1000 into 2, how many? 2000 Fermi farad is a load on this port. Huge load on the port. 2000 Fermi farad. Now, if you see the clock, this is the clock. So clock is becoming high means this capacitance has to be fully charged. clock is becoming low means capacitance will be fully discharged. As this capacitance value is very high, what is the capacitance value? 2000 Fermi-farad. It will take more time to charge, more time to discharge. Like your tank capacity, right? If your tank capacity is more time to fill. Tank capacity is less time to fill. As this capacitance is very huge, it will take more time to charge. As it is taking more time to charge, like this, it will take more time to discharge. Again, more time to charge, more time to discharge. So where is the clock signal here? Clock signal has become what signal? Almost triangle signal. Because all this time is wasted in what? Charging only. Actually, charging should happen very fast, like this. After that, it should become what? High. And discharging should happen very fast, like this. But it's not happening because of what? Huge load on the clock port. This is not happening because of what? Huge load on the clock port. Why there is huge load? Because one clock port is connecting to what? All nets. Now what you do? As one teacher is teaching all the students. As one teacher cannot concentrate on all the students. What in our childhood they were doing some groups, and for each group there was a leader. Right? Divide that entire thing into what? Different groups and make a leader. So similarly, as one port, if it is driving all the flip-flops, there is huge load. Because of huge load, normal clock signal is becoming what? This should be the normal clock signal, like this. Normal clock signal is becoming this type of signal, triangle signal. So because of that, what we do, we build a clock tree. So this clock port now, this clock port now connect only one buffer. Now what is the load on this clock port? Only this net capacitance plus what? Pin capacitance. Only 2 Fermi-farad.
Okay.
Only 2 Fermi-farad. This net capacitance plus what? This pin capacitance. Now at this buffer, the clock will charge very fast. Clock will discharge very fast. You are getting proper clock here. Again, this buffer is driving these two buffers. Again, this buffer is driving these two buffers. These two buffers. Again, this buffer is driving what? These three flip-flops. This buffer is driving these three flip-flops. And again, this buffer is driving this buffer. It is driving these three flip-flops. Alright, this is driving this buffer. Right, this is driving this flip-flop. So I will redraw this diagram. Right, here it is very small. Now this is converted to like this, right? Now you have one clock port. From one clock port, what has happened? Now you are using one buffer here. From this one buffer, now you have one more buffer here, one buffer here. And from this one buffer, again what you are doing? You are using one buffer you are farming here, one buffer you are farming here. Again from this buffer. Again from this buffer, what you are doing? Again one buffer you are farming here, one buffer you are farming here. So what are the flip-flops present here? That is connected to this buffer. What are the flip-flops present here? That will connect to what? This buffer. What are the flip-flops present here? That will connect to this buffer. What are the flip-flops present here? That will connect to what? This buffer. Like that, each buffer will take care about. So now what we have done? One clock port was driving the all flip-flops. Now what we have done? This one port is driving only one buffer. This buffer is driving how many buffers? Only two buffers.
Two.
And this buffer is driving how many buffers?
Two
Two.
buffers.
And this buffer is driving only, you assume on 10 flip-flops. This is driving on 10 flip-flops. This is driving on 10 flip-flops. This is driving on 10. So we have built a clock tree. It's very small clock tree. In reality, we'll build very big clock tree like this. So what we have done, we have split the load on the port to buffers. So building a clock tree, right? So we build a clock tree to split the load on the clock port is called as what? Clock tree synthesis. So we will see. So what is Q? What is latency? How skew and latency is affecting clock tree synthesis. All those things we will discuss in advanced part. So after clock tree synthesis building, last step is routing. What is routing? Connect ports, macros, and standard cells by using what? Metal layers. How you should connect that, right? Keeping this as a reference, right? Your output of AND gate is connecting to what? Input of OR gate. So here also you make the same connection. In the layout you see where is output pin, right? In the layout you see where is output pin. Okay, here I have output pin. Here I have what? Input pin. So output of AND gate you make connection to what? OR gate. So make a connection. So here you have AND gate input. Here you have inverter. Output of inverter is connecting to what? Output of inverter is connecting to input of AND gate. Then make a connection like this. By using metal layers, you make a connection. However, connection present in the netlist, the same connection you do here. So after making connection, your routing is done. So routing happens in two steps: global routing and detailed routing. Global routing means rough routing. After that, my tool will do routing properly without shorts. What is short? If one routing is going here and another routing also going like this, what happens here? Then there is a short here. Same metal here. This is also M1, this is also M1. Then there is a short. So my tool first it will do rough routing. In rough routing there will be shorts. During detailed routing it will resolve all the shorts. So after routing we will do block level sign off checks or blocks. So majorly we have three types of sign offs. One is what? Timing sign off. In timing sign off we are having a major role. That is, we have to meet setup and hold violations. So we will do that STA. Static timing analysis we do. So major things what we meet in timing sign off is setup and hold violation should be 0. That you will understand what is setup and hold violations. Your max trans, max cap, max transition, max capacitance, max fan out violation should be 0. What are those violations? That you will understand. That we do by using a separate tool called as what? Prime time. See, physical design is done by using a tool called as what? Fusion compiler or IC2. That is from Synopsys. We use Fusion compiler or IC2. So these sign off checks are done by using separate tools. The tool name is called as what? Prime time. So whether all the timings are meeting or not, right? We'll check that. So mainly setup and hold violations, max cap, max trans, max fan out violations. Everything is meet. Everything should be 0. That we will validate in separate tool called as prime time. And spec extraction is done by using star RC. So that we will do after routing stage. Next we will do IR drop sign off. As I already explained to what is IR drop, right? So we will check voltage drop. That same example what I given, voltage drop. So whether we have more IR drop or not. IR drop verification cannot be done in physical design tool. Physical design tool is Fusion compiler or IC2 from Synopsys. For that we have to use separate tool to check the IR drop. That is called as REDOP. REDOP tool is used. So we'll check what is IR drop. If we have more IR drop, we cannot fix in REDOP. We have to fix in what? Again in physical design tool. Only to check what is the IR drop value. We use what? Red dot. But for fixing again, we have to come back to what? Okay, here I have more IR drop. Power planning should be done properly. So where I have to do power planning? I have to do power planning in red dot? No. I have to do power planning in Fusion compiler only again. Again, after changing the power planning Fusion compiler, make the changes in Fusion compiler. After making changes, again give this design to what? Reduct. It will check whether IR drop is reduced or not. If it is not reduced, then again change the power planning in what? Fusion compiler. Again check. After IR drop is coming down, then we will send this to what? Physical verification. So physical verification is done by a separate tool called as IC validator. So here we use a separate tool called as IC validator from Synopsys. IC validator is used as PV sign off tool. Right? Yes, I'll come to your question, Junaid. I'll come to that. So we are going to check DRC, LVS, and ERC, right? DRC, design rule check. See, Foundry has given the rules, design rules. See, during my routing stage, so between one metal layer to another metal layer, I have to maintain minimum spacing. If I'm not maintaining the spacing, my foundry cannot fabricate this metal layers. So foundry and minimum width of the metal layer I have to maintain. Foundry has given the rules. If I am not maintaining the foundry rules, my foundry cannot fabricate the chip. So checking whether I have maintained the foundry rules or not. That is called as what? DRC. Design rule check. Then what is LVS? Sangesh, I have already told you, right? Timing sign off means we are going to do setup and hold violations. Checks. Max cap, max trans, max fan out issues. So all those things you will learn in STA, static timing analysis. So we cannot explain in 5 minutes or 10 minutes. That requires 10 to 15 classes to explain everything. To explain static timing analysis requires 10 to 15 classes. So you will understand only what we do in timing sign up. Only we go to advanced classes. What is LVS? Layout versus schematic. So in LVS, what we do, all the connections present in the layout, right? I have connections present in the layout, metal connections. The same connections are present in the netlist or not. We will cross check. Here output of AND gate is connecting to what? Input of OR gate. The same connection is happening here or not. We'll check. If it is happening, no issues. This is layout. What is schematic here? I don't have schematic. This netlist itself is called as what? Schematic. Check the connections present in the schematic, that is netlist, and check the connections present in the layout. If both are same, no issues. If both are not same, then you have to debug why it is not same, where it is missing, what has happened. You debug and where to check it. That is called as LVS. Next is ERC, electrical rule check. All the electrical connections are proper or not in an IC, like tie cell connections, cap connections, all those things. ESD production cells are used, electrostatic discharge production cells are used or not. So all those checks is done in electrical rule checks. All those things you will study in detail. So these 3 sign off checks we do. If these 3 sign off checks are validated, then we extract the GDS file, and this GDS file will send for what? Fabrication unit. Now we will do physical design course right from synthesis till sign off checks. Lab is not done for IR drop sign off. Lab we will do for what? Timing sign off and physical verification. We are not going to do for IR drop sign off because we don't have redox tool. Only theory is done. Right? IR drop, physical design engineer will not do IR drop sign off. for sure. For everything, we have separate team in industry. But here we are doing it. But only lab in demo class only I'm telling lab is not done for IR drop sign. Theory we cover. But for timing sign off, we do lab as well as theory. For physical verification, we do lab plus theory. For only for IR drop sign off, we are not going to do the lab. So when we come to EDA tool, right? See, there are two EDA tools, Synopsys and Cadence. So institutes will be having only tools from any one of the vendor, either from Synopsys or from Cadence. So this is the only institute we have both the tools. We have Synopsys as well as what? Cadence. See, physical design course is done by using Synopsys. Physical design course is done by using which tool? Synopsys tool. But we will also cover Cadence after covering the flow by using Synopsys tools. 1 month extra will take. We'll cover even in what? Cadence. But the fees is different. Only if you want to opt physical design with Synopsys, it is something like 59,600. Even if you want Cadence, it is 69,600. Even you can opt at the last also, it's your wish. I think I have made it clear, right? About Cadence, see, we don't have course only with Cadence. We have course with Synopsys. So using Cadence is optional. Sir, if you tell, I already know the physical design, but just I want to learn the Cadence tool. Yes, then you can opt. If you already learned the physical design by using our institute, the cost is 10,000. If you want to opt only Cadence tool, then the cost is 10,000. I'm telling you, it is not a physical design course. Only we will tell you how to use the tool. We will not teach you what is floor planning. We only tell what is a command for floor planning. Only if you want to opt for the Cadence tool flow, the cost is 10,000. If you were the student of our institute, if you were means physical design you already done by using Synopsys tool from our institute. I'm telling for the students who already enrolled for previous batches, right? Then if you want to again want to learn Cadence, then the cost is 10,000. But if you're not done any course in our institute, then the cost is 15,000. That 5,000 discount for our students already done. And for the fresh students, its choice is yours. If you want physical design, it's physical design course is done only with Synopsys tool. The cost is 59,600. If you want to do along with Cadence tool, means it is Synopsys plus Cadence. You cannot do any time you want. You cannot even after 1 year. You should pay that extra 10,000. That's it. You are already part of our when you will complete Synopsys tool.
Sir, is it mandatory to learn both Synopsys and Cadence?
See, companies, I cannot name the companies, but companies use both the tools. Few companies will use Cadence, few companies will use Synopsys. Then it becomes your responsibility to learn any one of the tool. See, flow is important. The learning tool is, see, nowadays working in physical design is very easy because company has flow. Company has well-defined flow. Even you need not to learn each command. Flow will take care. What is the role of physical design engineer? Understand the issue, what issue you are facing, how to address that issue, right? How to address the issue, what is the problem, debug, right? That is what you have to learn. So adapting to any of the tool is very easy. It's not so very difficult, and it's your wish. So industry uses both the tools. They use Fusion compiler, few use Fusion compiler, few use Innovus. This is mainly for physical design, right? Yes, tell me.
Sir, sir, if you want both Fusion Compiler and Innovus tool, then how, and if we are a previous student, means how much will be the fee?
See, if you are a fresher joining today, if you're opting PD plus synopsis, the cost is 59,600.
Okay.
PD plus synthesis, sorry, it is not synthesis, it is synopsis. It's synopsis plus
Uh,
cadence.
cadence.
Then the cost is 69,600. 10,000
If
extra.
we are a previous student means,
Yes, I'll come back.
and
Let
we
me speak.
want,
I'll come
no,
back.
I understood. If we are a student, previous student, and we want both Fusion compiler and Innovus, only the
So
tool
you are
things,
previous student of which course?
physical design.
Then you already learned synopsis, right?
Yeah,
Then you
tool
can
once
take
again,
cadence. That is not possible. Again, see, tool is very costly. So, see, what
okay,
is the purpose of restricting the tool usage? I'll tell you. Tool is very costly.
okay,
Tool license is not so easy to get. Right? We are paying in
yes, yes.
lakhs to get a tool license. And the students, if we give them the tool, they are selling the
Mm-hmm.
tool. They themselves are creating the market.
Okay,
It's only username and password, right? If they give the username and
okay,
password, that is they themselves are selling the tool.
okay, okay.
Or they are giving the username and password for the candidates who are not registered to the course.
Mm-hmm.
One person will
Okay.
register and 10 to 15% will use the tool. For that purpose,
Mm-hmm.
not extend the tool generally, right? But on request, you can see the genuine cases, right? We will do it. You can talk
Okay,
to the office for that reason.
okay, sure.
See, cadence is not with 14 nm, cadence is with 45 nm, 45 nanometer. So
45.
TSMC, I think we have it is with 18 nm. I'm not sure. I have to check that.
Okay.
But cadence, we have like files for 45 nm, 45 nanometer.
But the industry level will be less than 16 nm and all, right? So that level of
Industry will be
knowledge will be
industry will be working at 3 nm, 2
3
nm.
nm.
But why,
Yeah.
sir? You are not. Why we are not using it? See, industry has
No, that.
MOU with their boundaries, right? Just
Mhm.
for example, I'll tell. If Qualcomm, if you take right, they have MOU with
Huh.
TSMC, VSM. So they will
Okay.
play in close for them. They will give all the input
Okay.
files required. So we cannot
Yes,
do
yes,
that.
yes.
So if we want to purchase from TSMC means the course fees will be like 40 to 50 lakhs.
Okay. No, if we want, just
We
we
have
need
to
the
define.
commands on.
We have to depend on the files given from the synopsis itself. We have to depend on the files
Okay.
given from Cadence itself. They have given only till 45. We can work only till 45. But we have enough experience trainers who can
Yeah.
tell you how to use it in lower technologies. What happens in lower technologies? Yes,
Okay.
you can
Okay.
ask me
Yeah.
doubt. Yes, you can discuss with me. Wait. Please ask me. What is your doubt?
Got it, sir.
Okay. So now you ask me your doubt. After 6 months, you can opt at that time also. You have done the course. Now, if you want to join for cadence, then pay 10,000 and join. Now you pay 59,000. At the last, you can pay 10K and you can join. If at all, they have not increased it, right? If they not increased it, so I'm not sure whether they'll. So it will be revised based on the. Yes, I'll come to all those things. Course structure, right? Synopsis, cadence, everything. I'll. No, I'm making it very clear, right? Cadence is not with 7 nm, and even synopsis is not with 7 nm, right? Synopsis is with 14 nm, and cadence is with 14 nm and 28 nm. Cadence is with 45 nm. We are also getting the files with 18 nm, but this is conditional. But 45 nm is correct. See, with nanometer, nothing will change. Rules will change, foundry rules. Flow will remain same. As tool, what you have to learn? You have to learn how to use the commands. If I ask the command for floor planning, you have to tell the commands. 5 nanometer, what happens? Rules will change. Right? That rules you can adapt easily. It's not very difficult to adapting for the rules. 3nm, you can adapt to the rules. But in the 3nm also the command remains same for floor planning. In 28nm also the command remains same for floor planning. In tool point of view, 28nm is also same, 3nm is also same. But complexity is different, right? In 3nm, cell size is very small. This is a cell size. And in 28nm, this is a cell size. This is a cell size. In small area, I can occupy 10,000 cells in 3nm. But in 28nm, I can occupy only 1000 cells. Because here cell size is what? Very small. In a small area, if this is a area, this area is fixed. In this area, I can occupy how many cells? 10,000 cells for 3nm. Because cell size is very small. But if I go to 28nm, cell size is very big. I can occupy only 1000 cells. I can occupy only less cells. So we have bigger area for 28nm, but for 3nm we have what? Small area. Yeah, every area is very small. And from some foundry rules, right? DRC rules will change. So we have more rules in 3nm, but we have less rules in 28nm. So only rules wise it will change, but flow wise and command wise nothing is going to change. Same commands you use everywhere. Now when you come to the course structure, see if you have any doubts, you please discuss outside or discuss with me, right? I cannot repeat this again, please note down that. See, this session is recorded and this is also given to the other candidates. So this should be clean. Yes, Junaid, you can do that. You can opt for PD plus synopsis first. Later, if you want to learn cadence, you can opt for cadence. Right? See, now currently the cost for the students who already pursued the course in our institute, it is 10,000. Later it may change. It is changing or not, I cannot assure. Right? It is not changing, you can pay the same 10,000, right? Or later they may change based on the market demand. If there is no demand, they can retain the same value. If there is high demand, demand means out we have 30 licenses, you assume, right? 60 students want the tool. Then we have to increase our cost because we have to purchase more licenses. You understood, right? If there is more demand, then that cost may got increase. Why it will increase? Because we have to purchase more license. Basic license will get with less cost, but if we want to get more license, we have to pay more cost. So if you have 30 license and no student is opting for cadence, you assume, then the 10,000 will remain same. But 60 students are opting for cadence. We have only 30 license. Then what is the thing? Obviously, we have to purchase what? More license. Purchasing more license, we have to purchase, the cost is different. After some band of license, the cost is different. Then obviously the cost also may increase. So that is, you make sure before joining only, right? You ask, discuss with the office, right? While paying the fees only, you can discuss with the office staff. They are not available today. Most of the staffs are not available today because it's Sunday. Tomorrow they are available. You can make a call, get clarity of this, then you can join. So specification of PC, right? There is even I have i3 processor. I am using it. If AMD is there, it's okay. So minimum, you should be having i3 processor, Intel i3. So if that is there, it's okay. See, there is no complex requirement of PC because anyhow you are not going to work in your PC. Through your computer you are going to connect to our server. Whatever design you are doing in our server. So any complex specification is not required. Means hi-fi laptop is not required. Whatever laptop you have, I think you can do it with that. But it should be in the working condition. So this is already done. Right? So this is what our core structure is, right? See, I'll cover my course structure. So later, if you have any doubts, you please ask me. So totally, our course is planned for 5.5 months. 2.5 months is for basics and advanced is for 3 months. It is not 3 months actually; it's 3.5 months. Okay, we have had 1 month for this one, right? Okay, fine. Fine, okay. I thought it's not added. It's added. So this is what our course timing duration is. So 2.5 months is for basics, advanced is for 3 months only by using synopsis. If you want again cadence, that is extending by 1 more month. So totally I can call PD advance is for 4 months if you want cadence. If you don't want cadence, it's only for 3 months. And basics is for 2.5 months. What is covered in PD advance? Whatever I discussed, right? Till now that all those concepts are covered in detail with lab. In PD basics, what is covered? These topics are covered in PD basics. Digital basics, GVIM, Unix and Linux commands, TCL basics, because TCL is very, very important because all these synopsis tools, right? And cadence tools, they can understand only TCL. Then CMOS basics, like what is your MOSFET, what is P-type semiconductor, N-type semiconductor, what is BJT, what is NMOS, PMOS, what is CMOS, what is layout, what is fabrication steps, what is FinFETs. All those things are covered in CMOS basics. Then in physical design basics, some small terminologies, what is core area, die area, some small terminologies we will cover. Then this is only for 1 day or 2 days, physical design basics. It's not very lengthy. Like what is cell delay? What do you mean by power? What are different types of powers you have? So these powers depends upon what factors. Cell delay depends upon what factors. All those things we'll cover in what physical design basics. Then we'll start with what? Advance. So this basics, when we talk about PD basics, right? These are class timings. You have only weekdays option that is happening from Monday to Saturday. Each date is for 3 hours. See, weekend is only on the request. So we don't have weekend classes. Weekend classes only on the request. If any candidate cannot attend on weekdays, if you want weekend support, we will do weekend classes. Only it is for the candidates who are already working, for working professionals. Only for them, this weekend is done. But generally, our course is happening only on weekdays. And we also give recorded videos. So we'll give live recorded videos. It is not pre-recorded videos. So I'm removing it. So we are giving this recorded videos. So whatever class done today, right? That recorded video is given to your portal. There is one portal. We will give one username and password. There we will add automatically. If I am completing class today by 12:30, around 5 o'clock or 3 o'clock or 4 o'clock, you will get the recorded video. We require at least 3 hours time to upload that video. Right? So every session, live recorded videos you will get. Yes, see, if I complete my class at 12:30, you will get the live record video after 3 hours. You will get at 2 o'clock or 3 o'clock or 4 o'clock. Before 5 o'clock, you will get. Then you can watch the live recorded videos. So live recorded video facility is given. If you miss the class by any chance, then you can cover it by watching recorded videos. Missing the class because of fever or some health issues or some other personal reasons, right? Then you can go with that. Then after PD basics, see, I please ask your all doubts. I will, if you have any doubts, you please posting in the chat box. I will cover up those questions later, right? I'll answer to those questions later. First, I'll cover the structure. Then we come to PD advanced, right? PD advanced, we have weekdays and weekends. Weekdays, only practical lab will happen. Lab or project, both are same. Only practicals will happen, right? That happens between Monday to Thursday. Every day, 3 hours. It is from 10 to 1 or 2 to 5. It depends upon the batch strength. If 90 students are enrolling for each batch, so previous batch has happened like that only. 90 students, 110 was the count, 110. So we cannot do at a time. Right? We have to split it to 2 batches. 110 students I cannot do from 10 to 1. Then we have split it to 2 batches. Morning 1 batch, afternoon 1 batch. So depending upon the batch strength and mentor availability, it will be either in the morning or it will be in the afternoon. It will be 10 to 1 or it will be from 2 to 5. That is only lab, Monday to Thursday. Theory, right? Theory is done only on Saturday and Sunday. Friday is holiday. There is no holiday on Sunday, right? For PD advanced, holidays on Friday, but theory is done on what? Saturday and Sunday. See, this theory is done by some expert lecturers, some working professionals. They will do the theory classes. So for that reason, it is done only on what? Saturday and Sundays. The theory session will happen between 10 to 1. There is one more separate lab session happens on weekends, only on request. That is weekend lab. The candidates who cannot attend on weekdays, if there are some working professionals who can attend on weekdays, then they can attend the lab on weekend at 2 to 5 p.m. Right? Weekday students will do the lab from Monday to Thursday, and Saturday and Sunday they will attend the theory session. But the working professionals who can attend the lab on Monday to Thursday, they will attend the theory on Saturday and Sunday morning. Afternoon they will attend the lab. Other students who are attending here, they need not attend here. If you are attending labs on Monday to Thursday, don't attend on Saturday and Sunday. Don't attend lab. Only attend the theory. So this lab is done if you mention that if you are working professional and you cannot attend. If you mention that, Institute will create a separate lab session for you on weekends. Right? So placement support. So placement support happens with regular assessment and mock interviews. And how do you perform? Right? See, we do regular mock interviews and assessments. See, if you're performing good in that, then we will add you to the. So we will do test and assignments in between. We'll give during the course. Then we'll do mock interviews. If you perform better in this, right, then we will also First, if you're performing better, then we will put you in the placement group. If you're not performing better, then you will be in the normal group itself. So we will post the placement related inquiries only in the placement group. Means if you're performing better, then only you are allowed to take the placements. Why? Because we don't want to send a non-prepared student in front of interviewer. If he is not answering properly, institute reputation will get damaged, and even the company may not come back to us. That is the main reason we are not forwarding any candidate to the placements without clearing mock interview, mainly mock interview. So you have to do that. So if you are not performing good, even after the mock interviews, multiple mock, if you're not performing good, then we have done repeated interview preparation sessions. So last week also we have done, last month also we have done 1 month interview preparation session, free of cost. We have not taken any separate sessions for that. We have seen, okay, students' quality is not good, they are not preparing good, they need some guidance. Then for every topic we have picked a few questions, we have discussed those questions and we have discussed how to answer it. That we have done last time for 1 month. Even we have done that many times. We have done interview preparation sessions. Once if you are forwarded to the placement group, we forward all the placement related information there. We will collect your resumes. We will forward to the companies and you will get direct interview call from those companies. So interview support will be given to you till you get the job. So there is no there is no restriction like you will get only 3 chances or 4 chances. Support is given till you get the job. Only your role is prepare well and clear this mock interview. See, we are not conducting mock interviews like industries, right? Asking very tough questions. We will ask the basic questions. Even though if you are not answering basic questions, we cannot help. In industry interview is uncertain. Uncertain means they may ask easy questions, they may ask tough questions, they may ask questions which is totally like practical oriented. So even those type of questions we have done in interview preparation. But in mock interview, our intention is not to filter the students. Our intention is to make the students aware what type of questions may be asked. So we are not asking very complicated questions intentionally. We make students even comfortable with simple questions. Don't expect that same questions will be asked in interview preparation, in final interviews. So even there will be questions from labs, everything, right? For that reason, we have done multiple interview preparation for the candidates who are not cleared interview and for the candidates who are already cleared the interviews. For both of them, we have done the multiple interview preparation sessions. And if they need any separate one-to-one mentoring, we will assign one of our mentors to support you. It is not for entire 3 months. Only when you have queries. See, this is about our placement support and interview preparation. And only about placements. When you talk, right? We have multiple companies tied up with us. If they have any requirements, they will ask. They will come to us. We'll collect interview resumes from you and we'll forward to them. So the package, starting package, it depends upon the company to company. If it's a product-based company, they pay very good. What are product-based companies? Intel, AMD, Nvidia. So our students are placed in Intel, Nvidia. You can see the notice board, right? I think they are removed or not, I don't know. Yes, if it is product-based company, the package is good. If it's service-based companies, right? What is service-based companies? Service-based companies will hire you and they will make you to work on the projects about product-based companies itself. When they hire you, they may not pay you very good. They may pay you 15,000. When you go to the project of product-based companies, right? They may pay you good salary, like 40,000 or 50,000 per month. So that depends upon your capability. How much time you will take to work on the client projects. The service-based company will hire you and they'll put on the client project. So from the service-based company to the client project, how many days you will take? That depends on you. If you're very good, smart enough, you can clear the client also will do one interview. That is called as what? Client interview. If client interview you are cracking very fast, if you're doing within 1 month, you will get very good salary within 1 month. So till that they'll give you the basic salary, like 15,000 they'll pay you. They'll not pay 40,000 or 50,000. So once you are onboarded to the project, from that point they will start with a salary of 40,000 or 50,000. Right? That is how the pay pack work for VLSI. It's for every candidate, irrespective of any institute. The same thing works out. So if you are placed in product-based companies, the product-based companies will not be having this type of strategy. Directly the pay scale starts with good scale. It's almost 60,000, 70,000 per month. The package starts with that. So VLSI, Physcial Design, right? 1 month, 1 year, or 2 years. First 2 years is always a struggling period in the time because till you are having enough experience, right? Till you are having enough experience, right? Especially in the role of VLSI, you have not given more importance. Once if you have 2 years of experience, right, your demand will I can tell in simple words, your pay scale will change like anything. See, in software, hike will be 7%, 8%. In VLSI, after 2 years, the hike will be 30%. Hike will even go to 30%. This year, a person who is earning 8 lakhs per month, 8 lakhs per year, next year, even he may get 16 lakhs per year. Means the salary is doubled, 100% increment. But it all depends upon your performance also. If you go to project and if for everything you go to your lead, I'm having this question, I'm not understanding, right? If you have problem and if you reach, it's okay. But everything you cannot go to your lead and asking, I'm not understanding. Then it obviously, if you are very talented, it's you obviously will get very good package, right? So with this introduction on physical design placements, right? I'll end my session and I'll open to few queries. So remaining queries you can text to VLSI Guru WhatsApp numbers, so they'll respond to you. So I'll come one by one. See, tool. See, we have two things, right? Tool is given 24/7. You can use. So there is no restriction that you should use tool only this much hours. So one tool access is given, you can use 24/7. Right? So advanced tool will start only during the advanced class. We will not give during the basics time, right? So advanced tool we give only after what? After 2.5 months. So during basics, see, basics is not only theory, right? Digital design is only, it's like a presentation type. Presenter will be presenting, you will be following, but you have many exercises there, right? But GTM, it is hands-on. It's not a presentation type. Even mentor will do, you will also do along with them. You will also execute those commands. Unix is hands-on. TCL is hands-on. But only CMOS is theoretical. Apart from this, all these three are what? Hands-on. So you will do along with your mentor. So all these tools will tell you how to install. And when we come to PD Advanced, we will give you the tool. And this tool you can use 24/7. There is no restriction of hours, but you should be knowing how to use it. Initially it is difficult, but after that you can use 24/7. I am telling initially it is difficult because you doesn't know how to use. Once you know how to use, you can use 24/7. If you miss any classes, we are giving recorded videos. So recorded videos, I've already told you, live recorded videos is given, and that video you can watch and you can cover up. I am planning for online weekdays classes, sir. Can I attend lab sessions in weekends? See, in weekdays we have only labs. Basics, I repeat once again, right? What is your query? Basics, right? Basics generally happens only on weekdays. Weekend is rare case. If you request, we will do it on weekends also. But when you come to physical design, lab is done only on weekdays, but theory is done only on weekends. If you can't attend the lab here, then please attend here, right? Weekend. So this is done compulsory. We will do. Even there is one candidate, we will do. This you can opt. Either you can opt the lab in weekends or you can opt the lab in weekdays. See, record videos is given for everything. Recorded every class record video is given. Let it be lab, let it be theory, let it be basics. For every class, recorded video is given. Whatever class we are doing in day-to-day life, day-to-day classes, every class recorded video is given, even for lab. Yes, assessments are there, right? Periodically, we have assessments. See, company bond, obviously, as a fresher, you will be having bonds. I am making it very clear, right? When you are a fresher, you will be having bonds. If you're already experienced, no bonds. But when you are going as a fresher, surely you'll be having a bonds for 2 years, 3 years. Bonds will be there. How many months tool is given? See, tool access is given during when your PD advance starts, right? When PD advance starts, we'll give the tool. So PD advance is for 3 months, cadence is for 1 month, totally 4 months. For example, in 3 months, you cannot complete your lab for some reasons. We will extend that for 1 more month. 3 months is our course duration. I have completed my course today. You will be having tool access for next 1 month. Next 1 month you can use it to practice, right? Till that time you will be having tool access. Even for cadence also. 1 month we will do cadence tool. Next 1 month, not 1 month, next 15 days we will be having access for cadence tools. So synopsis tools, 3 months we'll do the course by using synopsis tools. After course completion, by using synopsis tools, next 1 month, if you want, we will extend the tool. Right? After 1 month, if you want to extend, then you should talk to the institute. The reasons, something and all, right? Whatever they, or you should pay the minimum fees after 1 month. No, basic happens only 3 hours, right? We have already mentioned. Basic happens Monday to Saturday, 3 hours. Advance happens Monday to Thursday, lab, 3 hours. Theory, Saturday and Sunday, 3 hours. If you can attend the lab on weekdays, you can attend on weekends, Saturday and Sunday. So if you are already experienced and if you want any job opportunity, you should please talk to the institutes. I cannot talk about all those things in open forum. So please talk to the institute and you can discuss what is the support you can get from the institute. Because it is irrelevant to others, right? It's only relevant to you. So you can talk to the institute. Either you can come to the institute and you can discuss what, because there are a number of points I can tell you how to follow, what should be done. So I cannot tell you here because that is irrelevant to others. So for that reason, what you can do is one day before joining or one day after joining, you can come to the institute and you can discuss with us what can be done and what support you need from the institute. Also, you can discuss with that. So institute can do support in all those aspects. Right? Or if you cannot come here, you can make a call. Right? Make a call to our manager and you can discuss all your support required as an experience. We will tell you if you don't know what to do. We will tell you what to be done. So you can make a call tomorrow to our team. They will guide you what to be done. So today most of our employees are on leave, but try for tomorrow. I have already explained. Yes, we will provide the notes. Right? Don't worry. Notes is given in the in-skill portal. Right? You can get the notes from there. We will also give the hard copy of notes. It will be posted to you. Right? Even we'll post the hard copy of notes to you. Soft copy is also given. Soft copy, I'm not soft copy given means it is not given to download. You can open in the portal, right? In skill portal, you can open the notes and you can use it. And hard copy of notes is posted to you without asking for any separate charges. I think it's included in your fees. Hard copy of notes is given. Soft copy is also given, but it will be in the portal. You cannot download it. If you want to download, then you can ask with the admin uh, for the permission. So Vijaya, see layout we are covering in CMOS, right? Please enroll for the course. So here in the demo class we cannot cover all the details of layout, right? Please enroll for CMOS. You will get complete details about the layout, everything. We are going to cover in that. So physical design requires compulsory. You should be knowing TCL, tool command language. Next, you should be knowing fabrication steps. You should be knowing what is CMOS. You should be knowing what is AND gate by using CMOS. How to write AND gate by using CMOS? I think everyone know. A dot B the whole bar. How to write by using what? CMOS. OR gate by using CMOS. At least AND and OR gate. Next, you should be knowing what is layout. This is covered in CMOS, right? You can please enroll for that. No, you have any doubts in the whatever explanation I have done? You can ask me. Any doubts you have in that? Yes, this month batch starts from tomorrow. From basics, GVIM, right? We start from tomorrow. So we expect laptop should be. You should bring your laptops, right? As I told you during your basic course also you require we require you should bring the laptops because basic course except digital and CMOS all are hands-on. You want we expect you to bring your laptops. See, analog layout we have, analog circuit design, I think we don't have. Layout we have, right? Analog circuit design like designing PLL, that is what you're expecting, correct? So we can, our trainers can just explain basic circuits, but not in, so we don't have that course especially, I can tell you. We have analog layout design course, but circuit design we don't have. See, you don't have any difference between online and offline. So now how the course is going on, right? Few students are attending offline and remaining attending online. In similar way, the class will go on. So there is no difference between online and offline. Only difference is you can discuss with the mentor after the class. If you're coming offline, you can interact with the mentor after the class hours. Even during the class hours, you can even offline student can ask the doubt. Even online student can ask the doubt during class hours. You can unmute and you can ask the doubts. As you're asking doubts now in chat box in a similar way, you can ask the doubts. But after the class hours, if you want to ask anything, you can. If you want to talk to the mentor, then you can come. You can do it in offline. How to do it in online? Every student is provided with individual official WhatsApp group. See, we have two groups. One is main WhatsApp group. In main WhatsApp group, everyone are present. All students are present. In that group, you don't post anything. We have one more WhatsApp group that is for every individual student. For every individual student, there is separate WhatsApp group. In that WhatsApp group, the student will be present. Not all the student, only one student will be present. Along with that, mentor will be present. Admin will be present. Manager will be present. Owner will be present. So you can post your queries in that group. Individual, I will call it as individual official WhatsApp group. For every student, there is an individual group. You can post in that. Yeah, I think we have enough desktops, right? Sangesh, you can talk to the institute regarding this. Whether they can see, generally no one requested us to for PC, right? Give the PC till now they're not done. If you want, if you can just talk to the institute and you can get it clarified regarding the desktop PC. But generally we expect the candidate should have laptop. See, it depends upon the batch strength, right? We will not have more than 35. So we will restrict till 35. The batch strength is 35. Batch count. No, no, even 125 comes also, we will admit, we'll split the batches. One batch will happen on morning, another batch will happen on afternoon. See, there is a first they'll do GVM course. For that reason only they'll do GVM. GVM is a small text editor. That is very easy. So they can do it. They can join after 3 days. The record videos are given. From the first starting, for the first day, record videos are given. If you can receive the record videos and you can cope up, then you can do it. See, GVM is only 2 days course. GVM, GVM, GVM is only 2 days course. After 2 days, digital will start. He can start from digital. He will miss that GVM, right? He can cover up some other time when he has time. For digital, GVM is not required. So intentionally, we are doing GVM at the beginning because students will be taking some time to join. Yes, online and offline mixed together, we have 35. See, speed requirement, at least you should be having 5 Mbps. In mobile phone, right? You can use our LAN cables, the LAN ports here. If you're coming to the institute, if you're not getting the mobile phone signal, you can connect our LAN cables, right? All those are LAN ports. You can get on LAN cable like this. Like this, you can get on LAN cable. You can then you can that LAN cable will hardly cost for 100 or 150 rupees. Then you can directly connect to that LAN ports, or you can request the admin to the Wi-Fi password. See, Junaid, all these things, right? If I can pay the installment in 5 months, right? You can talk to the team, account team. Right? I cannot clarify on this. Please talk to the manager or to the accounts department. You can post in your WhatsApp. Automatically, they will respond to that. Five Mbps is minimum. You need 5 Mbps. You will see little bit slow if 5 Mbps. So if you have 30 Mbps, it is far enough. So even if you have 5 to 10 Mbps, it will work. Okay, right. So if you have any other queries, please ask in your WhatsApp group. Thank you everyone.